Okay. Okay. So it's currently 3:15 a.m. I don't know if you can see it over here in the bottom right, 3:15 a.m. Um, and I am currently working on uh 3:15 a.m. And I'm currently working on my CPU. Well, I finished a lot of it. Um, or I think I'm done. Obviously, I have to test it and see what's going on. But we can walk through it real quick, and I want to talk about some issues I had. I guess while making this specifically. Oh no, I deleted that change. Um, Gen mem. It's fine. Okay, cool. So we obviously have our stoppable file machine.sv, which has our reset and clock in. So this really only has two physical pins on the FPGA, which is reset and clock in. At the moment, that I do have to add more when I add like my peripherals. But that's not something I'm gonna worry about like right this second, probably like tomorrow or the day after. Um, but yeah, we have a few logic like um well these I'm actually not sure if these would be wires or registers. I guess it would just depend on um where they're getting set. Um, but yeah, we'll talk about that in a bit. So we have a few different signals here. We have our reset N, which is just the negative or the inverse of our reset. We have our general memory. How this works is we have two kinds of memories. We have a RAM and we have a ROM. So the ROM is smaller. ROM is this, and this is static. So I can't write to this. I can only read. Um, so it holds 2 to the 11th, I believe, addresses. I think it's around I don't know the exact number, but it's much smaller because our general memory has 2 to the 16 generally addressable addresses. And you can obviously read and write to it during operation. But this is just where the code gets like flashed or stored. Mm, and that's going to be off of a basically a memory file. It defined what it looks like. We have our 12 megahertz system clock. I didn't really know what kind of clock to pick. Obviously, you have different options um, with this board. Look at our data sheet real quick. We have two clocks. We have a 12 megahertz crystal oscillator and then a 100 megahertz crystal oscillator. 12 megahertz is used to drive like the kind of the FPGA, while 100 megahertz is more used to drive. Where, do you remember why they said that? Oh yeah, the system clock with memory in of the DDR RAM on here. I haven't yet figured out how to use that, but that's hopefully coming soon. Um, but yeah, I just use a 12 megahertz clock for now. Um, Using an MMCM and not a PLL. Just because PLLs can't. They need a higher frequency than 19 to work. And then we have our CPU with all of our signals. I believe I took out my interrupt signal. And this would obviously have more signals when we get to our peripheral interfaces. But yeah, so we can just hop in. These three, imagine them as black boxes. They work because they work. There's no need to kind of get lost in how they work. Um, I mean, you can if you want to, but I'm not going to. So we can go from machine into CPU. So within our CPU, we have a few different things. We have our states init, fetch, decode, execute. And this is just enum at the top of the file. And we have our CPU module with a few different things. I took out my external interrupt. That's what extint stands for. And then we have all of our the approach I just had to go with here was because I kept adding on to my module like inputs and outputs, I decided to just name them here and then define them later in the file rather than define them here because that could get pretty big, long, and messy, and there's no need for that. There's our interrupt that I commented out. I'll add that back in sometime soon. Um, and we have a few different things. We have instruction information, so we have our opcode, V1, V2, and V3. This is just our X, imagine our X, Y, and Z values. That's what goes into the register file. We have our 12-bit value. So that's obviously you have your XYZ, but you just have the value too. So that gets passed to the decoder. And then we have an X temp and a Z temp. I'll explain what that's for in a second. We have some control signals here. And then we have our PC, which is 12 bits long, and our IR, which is 16 bits. And then obviously our state. And then we have some internal buses, our XYZ, and then our immediate value bus, which are 16 bits long. Our Y reg file bus, which is 16 bits, and then our ALU output. Now I'll explain why we have these, because you don't, if I pull up the schematic I had earlier, you don't see it on there. These different buses, you just kind of see X, Y, Z, and maybe immediate value. Um, but we'll get to that in a second. So we have our decoder here. Our decoder just decodes. I'll do a little more deep dive later. But we just pass our instruction register, our opcode. I believe this is the only input and these are all outputs. So it takes this and kind of breaks it apart into these values and does that as a combinational circuit and not as a uh, like clocked. I believe the only module in here that is clocked is like the CPU part, which is like this part. Otherwise, everything else in here is a combinational circuit. Um, yeah. And then we have a control unit. This was kind of difficult because as you kind of keep making it, you have to add more control signals. You like realize you need this or you need that, and you just kind of have to add it in. But what helped was we can actually open up the control unit. Let's see. I'll show you why it's a little messy. So we open it up. We obviously have everything defined here, which is a lot. Um, to define everything, maybe some extra. I needed some ALUN, um, and then an immediate. Where is that? Yeah, here. These aren't input outputs, but these are just local registers or local wires, because they're not within a clocked process. But yeah, you can see within our case statement, it gets pretty messy here. I have to do all this again and again. So basically what I did was we've seen this file before, which is like our overview, but I actually made a matrix for our signal generation. And I have a script that just kind of converts all of these into, 100, blah, 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 whatever, um, into uh, all of this. So I don't have to keep typing this up every time. Obviously, you do have to check it, but some things are pretty similar, like the ALUN and ALU type is the same for everything except for shift. I realized with shift, I had to add a load H flag, or sorry, not for shift, I mean for offload H. I had to add a specific flag um, to deal with how it works. And how that is obviously we have shift here, which just takes a value and then shifts it by it sign extends the amount you want to shift it by, and then it just puts that value on the X bus, and then the immediate of how much you want to shift on the Y bus, and then the ALU just shifts it. But with upload H, it's hard to load. I mean, it's impossible to load two immediates um, onto uh, one bus. Yeah. So what I had to do was I load the value, the 12-bit value onto the immediate bus, which goes to the AL, which goes to one port of the ALU. And then I have a load H flag that I set specifically only for this instruction. Perhaps there's a better way to do this, and I hope to figure whatever that way is out. But this is just the best I could come up with, sitting here basically. Um, I wasn't like planning it out. I was just off the dome. Yeah, you have your load H flag that comes in, and then we assign an op type, load H and op. And if we look at our little ISA reference table, we can see that load H is the first value. So it's just 1000. So all I did was I just took the load H, I made the op type a 4-bit opt, so it looks at all 4 bits of the op type now. So if it's load H is 0 for every other ALU instruction except for load H, obviously. So when load H gets us to 1 and our op is I set that to 000. So our ALU gets activated because our ALUN goes to 0 and that gets flipped up here for our ALU enable. So our ALU enable goes to 1 when we have an instruction with a 1 here, but specifically for load H, I had to make an exception and manually set that. But that's okay. And then our load H flag gets set. We go to ALU, so that becomes 1 with 3 zeros because these 3 zeros are the ALU addition time. So then we just shift it by 12 specifically, so we can do it all in one cycle rather than having to load, store, uh, put back on the bus, shift by 12. This makes it a lot simpler. And it's only like one more wire, really. Um, yeah. So that's the control unit. We have our load word, store word, um, jump. Uh, so our jump is cool because we just set our jump enable to 1, and that comes out. Here's our jump. Jump enable comes out here, JEN, and our JEN goes into our jump unit, and out comes a value called jump. And that value, we have our clock process here. Um, instruction adder equals PC. This doesn't seem right. That is not right. Yeah, I have to fix that. Um, oh no, this is the instruction address. No, that's fine. That's fine. It's fine. I might want to change that though. We'll see. So we have our m data out equals y. So that's just memory data out equals y. Fair enough. But yeah, sorry. Back to our jump unit. So our out jump, we do our init or initialize, where we just set everything and we can skip the code basically on the first thing. So we do the first instruction in PC rather than going to fetch and then adding 1, and then starting at the first address, so then 0. So we go to 0, we go to decode, IR equals instruction data, blah, 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 instruction enable. So it just, so this helps, I believe this latches the value. This is a test this, but this should latch the value. We set this to 1. We latch IR data, then we set it to 0. Um, and I'll explain why in the next cycle. But yeah, if our jump is equal to 1, we change our PC to the value, so that's the 12 bits. Um, and then we go back to fetch. We go to fetch. If we're not at the last possible value of PC, which if we are, we're just gonna go at the 0. Otherwise, we're gonna add 1 to PC. And by adding 1 to PC, so we add 1, we turn on instruction enable. So that value gets put on the bus. So we'll say it's one gets put on the bus. Um, instruction data gets latched. Instruction enable sends this turn to zero. Uh, yep. And then our state. Now that I think about it, maybe I don't need this. Well, okay, if I don't need it, I'll take it out. Then I'm walking through it a little more mentally. That's why I like making these videos. It helps me kind of think through my process. Um, yeah. So that's pretty cool. You have an ALU or jump unit or reg file. Now I'm not 100% sure this register file actually works. It's probably not a good thing to say. Um, I'm gonna do some more digging to make sure it does work. Um, I'm obviously gonna test it out too because um, I have a very cool system on how I like run a test bench and all these different like files. I'll make a different video probably like tomorrow or day after to talk about that. After I have the second part of it completed. I think it's pretty cool. I'm not really sure how other people or like companies do their um like their CI/CD for like this stuff. But I think the way I'm doing it is pretty cool. Okay, moving on. So we have our mux. Oh yeah, our muxes. We have some muxes in here to pick our registers. So our control unit has the ability to overwrite our like what register we're selecting for both our Z and our X to be one rather than whatever was put on the was put on the instruction uh I mean, inside the instruction value. So that's useful for when we are doing branch equals zero, branch not equal zero, or we're doing load high, because load high loads the highest 12 bits of R1 and BQ's branch of equals zero and branch of not equals zero both look at the value of R1 to determine whether it's zero or not to conditionally jump. Um, So I needed a way to force the register file to not look at whatever values whatever values inputted through or is outputted by the decoder, but use a different value. And then we have a Z bus select, um, which is used to decide between our ALU or memory output. And this is just if it's zero, we're going to use our memory. And if our ALU is enabled, we're going to use our ALU output to store back into Z. And then we have the same thing for our reg file Y, like our value from Y or the media value that we could provide. Um, that's like a general overview of how this works. It's not super complicated. I do have to make sure a register file works because it's basically just a 2D array uh, that I'm just assigning to the outputs based on the inputs. Um, but yeah, I guess this is the other clock process. But this is just a reset function, so it's not a huge deal. But yeah, so I'm gonna make a note of that, but I do want to talk about how I do like kind of testing because I don't know. I didn't like find a good way in Vivado to do like multiple test bench files and see my waveform outputs and find out what's wrong. It's still a little tedious, but I think it's a lot more sensible in the way I'm doing it currently. Um, so this is TB CICD. Um, and then I'll make another video uh going more in depth. We'll just make a and all this stuff. all the code is on my GitHub, which isn't very like a crazy GitHub or anything, but I am trying to put this all out there. Just no, I think it's cool. I think it's really cool that you can just do this at home nowadays and not need hundreds of thousands of dollars of equipment just to like do whatever. Um, but yeah, I'm trying to think. Did I have anything else I want to talk about? No. Oh, actually, no, I did. I did. I made this video for a very specific reason. We're gonna open up the synthesized design. No, we're just gonna open the design. I don't know what I changed, but it doesn't matter. I didn't change anything significant, so oh well. I don't like the different like files in Vado. I feel like it's just very messy in the way they do it. And it's really hard to find like a git ignore that's like valid. I found one, but you have to add stuff, remove stuff. It's a pain. Yeah, let's open up this. So, oof, I hope I didn't clear that from. It's fine. Worst case, we can change it. So I was just taking a look around my schematic that was generated because I always like looking at this stuff. It's pretty cool. Um, and you can kind of find inconsistencies pretty quickly. Um, but yeah, let's look at this. So a few things. Um, we have our clock, obviously, and then we have our reset. Important with the reset, we have this iBuff, and that helps it kind of be a like it's at it without that. I know you can't add it to the sensitivity list. I'm not sure the exact reason. Um, hopefully gonna find out, or I'm probably gonna search up after this. Honestly, I'm pretty curious. But you do need this for this to be added to the sensitivity list. We have versus clock. This looks good. Um, Now, if we go to our your instance name, this should be gen memory. This is what I changed earlier to the name. But we can see our address and our write enable are both set to ground, which is kind of weird. I was like, why? Like that doesn't make sense. They shouldn't be. And same with our enable for instruction memory, because it should all be like uh, controlled by the signals coming out of the CPU. Um, So I was like, I didn't know what was happening. So I like looked through all my code, and then I realized while I was working on uh, my linter, I ran the linter just to see if I could find anything that was obviously wrong. And I got a ton of these types of errors where it's like, oh, this has not been set. And I was like, oh, this is easy fix. I'll just set them all to zero so they can be changed later. But I forgot if I set something to zero, I'm really just latching it to zero. So we're just gonna, okay, great. I'll just tell you what happened real quick. But I set my init memory to zero. I set my enable read address. Well, I set all this stuff to zero, which is why it was all getting latched. But if I just remove the assignments and I just run the synthesis again, oh, this is gonna take a minute. It's fine. Um, in the meantime, actually, we can check out why we need um why we need the let's start off with the what is an IBUF. So synth design. Input buffer. There's a clock input. There's a no up buffer that passes the input to the output. And interesting. OFG's input buffer is automatic. Place the clock lines. Uh, input. Well, okay, I guess it's kind of like a protection thing too. Um, okay, cool. Oh, cool. All right, so this computer is done. We can just reopen this. Takes a minute again. I got my Fanta Zero Sugar over here. Pretty good. Pretty yummy. All right, so let's back up. Okay, we can see immediately that our. Oh, wait, why is that in the middle of nowhere? I am not comfortable with that. We have the name change, but our write enable is now connected to the CPU, and same with the R enable for unstructured memory. I am still a little bit. Where does this connect? Because this should connect to our X. Ooh, I don't know if I did that. I don't know if I did that. Let's check that out. Next. Nope. Perfect. Well, not perfect, not perfect. But I did not connect our memory address to the. Okay, cool. So our M address, let me just take a look at that thing I wrote earlier. Mm, okay, perfect. Our memory address is just gonna be um, on our X bus anyways. So we can just go down here. We shouldn't need anything else. This should just be assign M adder equals X because there's nowhere else it should be getting a value from. Now if we resynthesize all this, oh, so much synthesizing. No, no. Okay, queued, queued. Okay, we're, we're running our synth design right now. Um, this is like the thing I wrote earlier in the video. I don't know if you can really see it. I like the equation that I wrote. It kind of helps you like think about where the values come from, where it's going. Because it's just hard to think about when you think about it like just numbers, I guess, or like lines. But our X bus should be the only thing connected to our address. One thing I do want to do though is be able to have offset um an offset on our memory address. So if I let's say we have can I make it blank page as an option? So let's say we have like um in we're trying to access memory address, let's say 4. So what we do is similar to how MIPS does it, R0, and then you can like do 4. kind of. Yeah, and that would just be like a full four. It would add four to whatever values in R0, and then put that value into memory so you can like address based on offsets. That might be a future thing though. I guess. Oh, but that wouldn't be a very difficult thing, would it? Because well, if we just quickly, I want to talk you through how I would do it, just because I can. Let's pull this up real quick. So we can see for our load word, we still have 4 bits of 0. What we could do with this is we can have like an ALU, but that doesn't only add in between our X bus and our address. And one of the inputs is obviously whatever values on the X bus, and the other one is this 4-bit constant that we can pass in. Just a thought, something I want to do later. After I get this all working. But okay, let's go back to our schematic. Perfect. We can see we have our address 15 connected back to our CPU. So now everything is truly connected together. I don't see any floating pins. This is what the CPU looks like on the inside, which is pretty cool actually. We have our bus, we have our registers. This is a mess. I'm actually curious, how many lookup tables does it say? That's not bad. It is not bad. 369. I thought I would possibly need another um FPGA because this wouldn't be big enough, but I guess it's a lot bigger than I expected. Yeah, that's really good. Um Where's the schematic? Yeah, this is insane. Are there two of those? I don't even know what these these are opcodes. Where's my decoder? I'm curious. This is the ALU. Oh, this is the ALU. Very cool. I guess it's cool how all this gets like abstracted away. Like this ALU was probably the smallest part of this entire thing, but it looks huge. So many lookup tables. Very cool. Yeah, this is insane to think about. Where is that decoder though? I'm very curious. Is this it? No, it's a junk unit. I guess this is the decoder just kind of sitting around here doing chilling. Um, these random. No, no, that's the PC program header. PC. Oh, that's very. Wait. Let's navigate this and find the CPU. Oh, damn! It's not even on here. What about no control unit either? PC. Yeah. Okay. What are the network? It's gotta be in here somewhere. Let's look for an enable signal. How are there no? I feel like I'm. This is not enough enable signal. Okay, we'll do. Is there memory in it? Okay, ALU enable. Where is that coming from? Okay, interesting. So is there a decoder in here somewhere? Oof, this is huge. Um, Memory load age. This might be the decoder too. I know it says a reg file in here, but I guess I compiled everything down to make it a little simpler. Very nice. Okay, cool. This is wow, this is huge. But yeah, so next step is to assign pins for my clock and reset, and I also need to get some of these. basic like memory files, and I can just those are very easy to add. You can just put IP sources, or well, not here. I go to here, hit this, I get this interface, and you can just load an init file, um, with whatever. I always need to make one. I need to learn what these COE files are, and how to make one. But yeah, so next is I'm just gonna make a very basic one, and then I'm gonna try and make a compiler in Python, not C. And they can just do some basic like uh, well, not a compiler, a assembler in Python. So it shouldn't be too bad. But yeah, cool. All right, so this looks about done. I'm just gonna go ahead and commit this. And then it's 4 a.m. It's nap time, so I'm gonna take care of that. Bye.